Alcohol reactions in chapter 11, and we got to this point, and I think we were all tired, and we were talking about making tosyl esters. Let me clarify what the slide is saying, because the slide kind of throws a whole bunch of concepts together. So let's look at an alcohol. And if I react this with a nucleophile, so that my alcohol is acting as an electrophile, I'm expecting an attack here. Well, a pair of electrons goes here. Actually, this pair of electrons goes here. And I'm expecting to see this product plus hydroxide as the leading group. And we decided that that's not a good thing. But, I decided it and shared it with you. Why is that not a good thing?
It's not a good leaving group because...
yeah, hydroxide is a strong base. It's a bad leaving group.
Oh, okay.
And so I can't simply take an alcohol and attack it with a nucleophile and expect anything useful to happen, because the alcohol is such a bad leaving group. That's what this slide gets to. So there's two ways to make this work better. One thing I can do is I can take my alcohol and put it in acid, and what will I get?
It'll water. It'll come off.
Yeah, I'll protonate the alcohol. And so now, this guy is carrying a positive charge. Okay, and this is actually a good leaving group. It's not basic, it's neutral, it's stable, and those are characteristics of a good leaving group. Now I nucleophile. Attack here, this goes off, and I have water as the leaving group, and I have the substitution. And so we can prime an alcohol to make it a good leaving group by either putting it in acid, or, as is suggested here, converting it to the tosyl ester using toluene sulfonic acid, which is this guy. Now, it turns out that we can't do toluene sulfonic acid directly and get good results. Okay, it turns out that taking off this hydrogen and this OH from here is an equilibrium system that actually doesn't favor the product side. And so there are ways to do this that we'll learn a little bit later on. But ultimately, this ester, and this is the ester linkage right here, having the alcohol exist as an ester, with an ester linkage, makes it a great leaving group. Because if this thing comes off as the tosylate ion, I've got stability associated with it. And I think we did talk about this a little bit, didn't we? Okay, and the tosylate ion then, or the tosylate leaving group, is a good one. It's not basic, very, very weak basicity, and it's very stable. And it's stabilized by what? Resonance. And so converting an alcohol to a tosyl ester sort of primes it for further reaction. That's the whole point. And again, the reaction, as is summarized here, is not how we really run it. We actually run this. This is actually a chloride here. We use tosyl chloride. The alcohol attacks, HCl comes off rather than water being split out, and that turns out to give us real good yields. Okay, and we'll talk about tosyl chloride a little bit more later. Now, in fact, here's tosyl chloride. So I take my alcohol and react it with tosyl chloride in pyridine. And what did we say the pyridine was for?
It's a base.
It's a base to neutralize the HCl that's produced as part of the reaction. Let me show you this. I don't know if this is in the slides. Here's my alcohol. And let's do the tosyl chloride. It will look like this. Now, this guy will attack here. Oh, a pair of electrons goes out here. And so the first step in this process will be the formation of this guy things attached to it, alcohol. And then the benzene ring, CH3. Now, at this point, this is going to lose one of these four things, and there's something that's really a great leaving group there. What is it? Chloride. And so this guy will take its pair of electrons and leave his chloride ion. This will come back in and recreate the double bond that was right here. And what I'll have here is a chloride ion, and I'll have the tosyl ester. Chloride comes off and ends up with the hydrogen from here. Chloride, in fact, I should probably show that here. This guy's carrying a positive charge. Chloride comes around and takes the hydrogen off and produces what? HCl, hydrochloric acid. And the pyridine that's in there is there to neutralize the HCl that's produced. And that serves two functions. Number one, it tends to get rid of a fairly nasty gaseous acid that's produced in the reaction. It also helps pull the reaction to completion, because this reaction is a bit of an equilibrium. But if I remove, remember Le Chatelier's principle? If you remove one of the products in an equilibrium, what does that do to the equilibrium? Pulls it further to the product side. Does that make sense? And so this pyridine will function in that fashion as well. So it neutralizes a noxious byproduct, and it pulls the reaction to completion. All right? At any rate, once we've created this, excuse me, the tosyl ester, now a nucleophile can attack here. The tosyl ester takes off because it's very, very stable. It's a great leaving group. And substitution takes place because we have primed the alcohol by making it a tosyl ester. How are you doing? Does that make sense? This also primes it for elimination. Remember, an elimination reaction will have a leaving group coming off of one carbon and hydrogen removed next door to make an alkene. So the tosyl ester is capable of helping us, facilitating the production of an alkene as well.
Oh, because that pyridine, the nitrogen on it, does it try to pull off that hydrogen too?
It could. Yeah, it could. In other words, the HCl wouldn't form. The pyridine could be the base that takes the hydrogen off.
Yeah,
and the chloride.
right on.
It doesn't really matter because it gets to the same point in the end. So how are we doing? Now, having examined, and this is an example of the usefulness of the tosyl ester in a substitution reaction. Here's my nucleophile, iodide, which is a good nucleophile. Here's my tosyl ester. In this particular case, I've got a tertiary alcohol. Actually, it's a secondary alcohol. I attack backside in an SN2 reaction. Iodide attaches. A pair of electrons from the iodide ion form the covalent bond with carbon. At the same time, the tosyl ester comes off. This is the tosylate ester that's released, or the tosylate ion that's released as part of the substitution reaction. Looks like this. And you can see this negative charge is going to be resonated over all three oxygens, which gives us stability. Is that making sense? Kind of a summary of reactions that can be performed with these tosyl esters. I can react the tosylate with hydroxide and recreate the alcohol. It's kind of a pointless effort because you use the alcohol to produce the tosyl ester. Hydroxide ion will displace the tosylate ion just to recreate the alcohol. I can take the tosyl ester and react it with cyanide, good nucleophile, and I can create a nitrile. It's a carbon-nitrogen triple bond. These guys are very useful. Notice what this has done is it's added a carbon-carbon bond to the structure. Where the alcohol once was, I now have a bond to carbon. And the cyano group, the nitrile, can be placed in acid and warmed in acid, and this will become a carboxylic acid. So I can actually use this as a way to create a carboxylic acid. I can react my tosyl ester with bromide to get an alkyl halide, an alkyl bromide, or chloride or iodide. I can react it with an alkoxide. This is a good nucleophile, and look, what we've got there is an ether. This is a pathway to make ethers, potentially. I can react my tosyl ester with a weaker nucleophile, but still, because this is such a great leaving group, even a weak nucleophile like ammonia will work, and I'll get an amine salt. Okay, the amine salt can be simply neutralized with acid, or excuse me, with base, and turned into ordinary amine. So this is a pathway to amines. We've got a whole chapter on amines coming later this semester. I can react the tosyl ester with lithium aluminum hydride, which is what?
It's a organo.
Strong reducing agent.
agent. Yeah.
It's a source of hydride ion, and the hydride, H-1, strong nucleophile, it attacks hydrogen here, tosyl ester comes off, and I've essentially taken it down to the alkane stage.
Right.
This is how we can reduce an alcohol all the way down to an alkane. We mentioned this as a potential. Again, you remember when we did, this is how it's done. There's other ways. I can dehydrate it, make it into an alkene, and add hydrogen to it. But this is a more direct way.
But there's no reason for that, right? Once again, you said alkanes are worthless, sort of.
Yeah, alkanes are not nearly as valuable, but I might have some sort of a special research need where I want an unusual backbone, alkane backbone that I can't get any other way, except as an alcohol precursor to get there. And this could be useful from that standpoint. Now, reducing alcohols, we just looked at a way to do that. Two different ways. I can take the alcohol and treat it with sulfuric acid and dehydrate it to make the alkene, and then with catalytic hydrogenation, I can turn it into the alkane. There's some issues with this, however. See if you can remember what issue you might be talking about.
Let's think.
What is the mechanism for this involved? We protonate the alcohol, make it a good leaving group, right?
Okay.
And if the alcohol comes off, it leaves behind what?
Oh, carbocation.
Carbocation. And what are they notorious for doing?
Rearrangement.
Rearranging. And so this method will work as long as we don't have to worry about rearrangements, potential for rearrangements. If that's the case, then we can go fairly simply to the alkane. The method we just described is to convert our alcohol using tosyl chloride, tosyl ester, treated with aluminum hydride, and we go to the alkane, an alternate reduction method. Does that make sense?
So is there one that won't suffer from rearrangement?
This one here.
Okay, so
No
that's
rearrangement here. Yeah, notice that there's no bonds broken to carbon except right at the end where hydrogen replaces it. And so there's no carbocation formed, and so that potential is removed from the possibilities here. What this should be, I don't want to jumping right off the page or off the screen at you, but what this should tell you is that alcohols are really useful substances. Not only do they have a variety of useful reactions that they can participate in themselves, but I can convert them to tosyl esters and do a whole host of things that allows me to use alcohols to get into carbonyl compounds, to carboxylic acids, to amines, other really useful substances, and very